Okay, Zoom is preparing to stream the webinar to YouTube. Okay, that's working. I'm going to come back. All right, and now I'm going to turn on the recording, start broadcasting my title slide, and then I'll let you know when you're ready to start, Shantanu. Okay, everybody ready? All right. So. Okay, Shantanu, over to you.
Okay. Hello, everyone. Good morning, good afternoon, wherever you are in the world. And welcome to the Monday, October 26th press conference of the first ever virtual DPS. I'm Shantanu Naidu. I'm the DPS press officer. And with us today is also Rick Fienberg, who most of you know is the AAS press officer. He'll be helping us with the Q&A and any technical issues that come up. So we're recording this briefing and it's streaming live on YouTube on the AAS Press channel, where it'll also be archived for future viewing. I'll begin by giving brief introductions of the panelists and their topics. They'll speak in order and then we'll move on to the Q&A. I ask all the attendees to type their questions using the Q&A features. But be sure to indicate your affiliation and which presenter your question is directed toward. And you can comment on other people's questions and upvote them to raise them in the queue. We've asked our presenters not to answer any questions via text while other presentations are still ongoing. And they'll answer those questions live during the Q&A session. Okay, so with that, let me introduce the speakers. Today we have Eliot Young, who will talk about increases in Pluto's haze opacity and column abundance from 2015 to 2018. We have Tracy Becker, who will talk about investigating asteroid Psyche with HST ultraviolet observations. Then we'll have Dave Tholen, who will talk about detection of Yarkovsky acceleration of Apophis. And then we have Ballouz, who will talk about craters on Bennu's Boulders. And with that, I'll let Eliot take over for the first topic.
Thanks very much. Let me share my screen. Can people see this? Does silence mean yes?
Yeah, we can see it.
Okay. So what we did is we observed Pluto as it moved in front of a bright star. For the last couple of years, Pluto has been in a crowded part of the sky over the galactic plane, and there's been some reasonably good opportunities to watch Pluto move in front of a bright star and see its atmosphere backlit for about 2 minutes at a time. And it's a rare chance to see what kind of structure you have in Pluto's atmosphere and what kind of particles might be attenuating light. You see this as the star gets backlit. There are two things that we wanted to look for with this event. One, has Pluto's atmosphere changed? Is it getting thinner or is it getting thicker? It's kind of strange, but here's a picture from Eric Meza's recent paper. Over the last quarter century, Pluto's been moving away from the sun. It's been moving far enough away so that over the last quarter century, it's about 10 or 12% further away from the sun. And as a result, it gets about a quarter less energy from the sun. You'd think that the planet as a whole would be getting colder. And yet its atmosphere, which depends on the surface temperature of nitrogen ice on Pluto, has been getting thicker. It's been roughly doubling every 10 years over the last 2.5 decades. So we don't understand what's going on, but we suspect that there's heat underneath the surface stored up from the past half a Pluto year that is keeping the surface from cooling the way it would if it were just radiating its heat away to space. Still, we expect that a cool down is imminent, and we're waiting to see, is the atmosphere going to freeze out? And if so, when? So we had a prediction for an occultation, and these days predictions are really good. In the old days, we didn't know where we were going at the 1,000-mile level, but now we know where we're going, in part because the Gaia catalog tells us where stars are really accurately. And after the New Horizons flyby, we know where Pluto is in the sky. So we can get the relative positions of stars and Pluto really pretty accurately. In this case, in fact, our errors were at the 10 or 20 kilometer level, which is just orders of magnitude better than we've been able to do in the past. And the prediction, you can see, showed that the center of Pluto's shadow was going to cross through Baja, Mexico and Texas, and then up towards the eastern seaboard. And this red line is the place to be, right in the center of the shadow. And we were lucky enough, we set up a picket fence of observers. We were lucky enough that 2 of them in Texas were really quite close to the shadow. And when you're close to the shadow, you can see a phenomena that we don't usually see, called a central flash. And here's what they look like. Let me see if I can show you a picture where we don't have the model overlaid. This is data from Lake Corpus Christi State Park. And right in the middle of the event, when the star is smack behind Pluto's solid body, you actually see a bright flash. And it's not a diffraction effect, it's a refraction effect. Parts of Pluto's atmosphere are refocusing rays, and there's a ring around Pluto's atmosphere that sends light to a central flash. And if you're close enough to the center of the shadow, you can pass by it. And that central flash is very diagnostic of haze opacity. Its amplitude really gets bumped down if you've got haze in the atmosphere. And the shape of it is indicative of the bulk abundance and temperature profile of Pluto's atmosphere. Let me show you a cartoon that kind of describes what's going on. Imagine that you've got a magnifying glass here, and rays from a distant star come through. They would get focused to a point, and you'd have a nice imaging system. Like a magnifying glass, rays from a star get bent towards the center by a planetary atmosphere. But it's not a very good imaging system, because rays that go closer to the surface get bent more than rays that come far from the surface. If you try to build Pluto's atmosphere as a lens out of glass, it would kind of have this funny bowl shape with the center blocked out from the solid body instead of this magnifying glass. So you wouldn't use it for any imaging purposes, but it's kind of interesting to think, what would it look like if you tried to build it? Now, as a star passes behind Pluto, bundles of rays get spread out, they diverge. And so even if you had no clouds, no haze, no stuff that absorbed light, you would still see the star get fainter and fainter, just because of this phenomena called differential refraction. The rays diverge. So there's been some controversy in the past. Do you have haze or not? Was it differential refraction that made the star dim, or was it haze? So we looked at this with our models to see if we could distinguish the 2 phenomena. And basically it turns out that some parts of the light curve, the star gets fainter and comes back, some parts of the light curve up here are barely sensitive to haze. You're probing too high in the atmosphere. Other parts are sensitive to haze and to the amount of atmosphere you've got. So when we look at just that shoulder region, what we call zone 3, you can see that we look at chi-square. We fit different models of the atmosphere. We look at the fits as a function of Haze optical depth and as a function of surface pressure. And in this case, you can change the Haze optical depth and the chi-squares pretty much fall on these vertical contours. It doesn't make much difference if you change the haze, but it does make a difference if you change the surface pressure. And we find a little bit of difference from ingress and egress, but if you combine them, the chi-square minimum is at 11.4 microbars. That's in August 2018, just about 3 months after the New Horizons flyby in July 2015. And according to David Hinson's radio occultation paper from 2017, the surface pressure that they use as their reference pressure from the radio occultation was 11.5, virtually the same, certainly within the error bars. If, on the other hand, the surface pressure continued to increase at a rate of doubling every 10 years, you'd expect it to go from 11.5 to about 14.4, which is just barely a significant change that we can rule out at the 3 sigma level. So we think that the surface pressure is very similar to what New Horizons found, and it may be the indication that we're starting to roll over and have the freeze out begin to occur. It bears further observations. With respect to the haze, I'm going to switch screens just for a second and bring up this figure. There was some circumstantial evidence that Pluto's haze was responding rapidly to the ultraviolet flux coming from the sun, especially wavelengths shorter than Lyman alpha, where it could produce nitrile radicals, which are thought to be haze precursors. And we had 4 occultations and the New Horizons event, which we've overlaid on the solar cycle. And at least there was circumstantial evidence that the haze seemed to follow the solar cycle closely. But the solar cycle continued to decrease from 2015 to 2018. And instead of seeing a decrease in haze, we actually see a slight increase. So it looks like correlation does not imply causation. It looks like this might have been a coincidence, and there are other factors going on. And the question now to look at is, what are the timescales of processes that form haze and take them out of the atmosphere, and are they longer than the 11-year solar cycle? And we think they are. So that's that. Thanks very much.
Great. Thanks all. Can you hear me?
Yep.
Yes.
All right. Let me share my screen. Okay, everyone can see?
Yep.
All right. Okay. Hi, everyone. Thank you for your interest in our recent work on studying the asteroid 16 Psyche in the ultraviolet using the Hubble Space Telescope. My name is Tracy Becker. I'm at the Southwest Research Institute, calling in from here in San Antonio, Texas. This paper, I'm glad to say, was just released today. So if you have any questions, please feel free to look at the paper or email me with any follow-up questions. So first, I'll start off with why we were interested in studying Psyche. This asteroid is thought to be primarily composed of metallic iron and nickel. This assumption about the asteroid has been made from various observations, including the high reflectance observed from radar observations from the Arecibo Observatory, as well as different properties, including its mass and the way it reflects light in the visible and in the infrared. That in itself obviously makes this asteroid extremely interesting. If you can imagine even this artistic concept of what a crater might look like when you have something smashing into a fairly metallic object, it's something kind of fun to even imagine what it might be to see it up close and in person. But more than that, it actually tells us a lot about how our solar system formed, and it has implications for even something deeper within ourselves, within our own Earth. Because the idea behind how you get sort of this chunk of metal possibly out in space is that it was actually originally part of a planet that was forming. And it had, just like on the Earth, where the metallic parts of the material that's coming together can sink to the center and form a core, and then you get more rocky stuff in the mantle and in the crust. That's what we think may have been one of the hypotheses for the history of Psyche. And so what could have then happened is that through a series of exciting collisions in space with other asteroids, the mantle and the crust were torn away from this protoplanet Psyche, revealing the core that was inside. So not only does studying Psyche give us information about perhaps the beginnings of our solar system, how planets form, and the subsequent collisional environment that it might have been in, it also provides what a lot of people like to refer to as a window into the core of planets, including our own Earth. And of course, this makes it a really interesting place to go visit. And so there is a mission planned. NASA's Psyche mission is expected to launch in 2022. And the idea is that this is going to visit not a rock, not an ice world, but a metallic world. And of course, there's going to be a lot of really interesting results when the Psyche mission gets there. In the meantime, though, there's actually been some evidence for perhaps a higher percentage of rock than initially thought, some evidence for even hydration on the surface. So the exact history of Psyche is still unknown. And I think that's what makes it even more exciting, because there's still so much that we're going to learn when we get there. But even with the Psyche mission at Psyche, there's no UV instrument on board. And so we wanted to look at Psyche at part of the electromagnetic spectrum that had not really been observed before on Psyche, to see what else we could learn. And so we used the Hubble Space Telescope to look at Psyche in the ultraviolet. These are the deepest into the ultraviolet observations that have ever been done on Psyche. And this can only be done from space, because we cannot observe anything in the ultraviolet from the ground. And so we got to go further into the UV, shed some new light on this object with the goals of learning more about what it's made of, and also to look for any kind of changes or processing on the surface, because the ultraviolet wavelengths are actually most sensitive to what's happening at the very, very upper layers of a planetary surface. And so first, what we looked at is it metallic? Our results show that the way Psyche reflects ultraviolet light is very similar to the way iron or metals reflect ultraviolet light. So this was sort of nicely in agreement with what a lot of these previous observations have said. However, I put a big caution sign there, because we did a bunch of computational modeling, and we showed that you only need to have sort of a sprinkle of about 10% of iron mixed in with other materials, depending on the grain size of these particles on the surface, and it could still end up looking completely metallic. So the iron kind of can dominate that UV spectrum a little bit. However, still in this line of possible more evidence for metal, we did detect reflectance features in the UV that could be signs of iron oxides or oxidated iron. This is the first time that these signatures have been seen in the UV on an asteroid. And so this again leads to more evidence that perhaps, we are seeing a good amount of iron, which isn't terribly surprising on Psyche, but it's still filling out the rest of this story about the asteroid. One of the great things about using the ultraviolet is that we can look at some other things that might be happening on the surface that you don't see as easily with other instruments. When we got deeper into the UV, we actually saw the asteroid start to brighten again. And when we've seen that on other asteroids, sometimes it has indicated perhaps the start of a feature that could tell us about the composition. But oftentimes we see this on planetary surfaces, and we equate it to having some sort of processing on the surface by charged particles from the sun, known as the solar wind. So we believe that this is basically weathering of the asteroid, causing an increase in brightness when you go deeper and deeper into the UV. And so, yeah, I will conclude by saying that we've shed new light on the asteroid 16 Psyche. These observations are going deeper into the UV than any previous observations of this asteroid. And like I said earlier, it does reflect light in a way that's similar to iron, with that caveat again that we don't know exactly how much iron must be there based on only these results alone. But these are the first UV signatures of oxidation iron oxides on an asteroid. And we do see that Psyche brightens in the deep UV. We get this blue slope in the spectrum, which could indicate processing of the surface by solar wind. Thank you.
I guess I'm up next, right? My video is being inhibited by the host.
Oh.
There we go. Okay. So let's start the screen sharing. Are we good?
Yep, I can see it.
Okay, great. I'd like to tell you about our detection of Yarkovsky acceleration on the near-Earth asteroid 99942 Apophis. Okay, well, as the title suggests, the news is that we've detected Yarkovsky acceleration. And what made this possible is a superb set of data that we acquired with the Subaru telescope earlier this year. We had 3 nights in January and 1 night in March. And altogether, we collected 18 exposures. And I was flabbergasted when the astrometric quality of the data turned out to be better than 10 milliarc seconds for each observation. So when you have 18 observations, good to 10 milliarc seconds, that's, in terms of random error, that's equivalent to a single position, good to about 2 milliarc seconds. And at the distance that Apophis was from Earth on January 25th, that is equivalent to about twice the size of the asteroid. This asteroid is roughly 300 meters in diameter, and 2 milliarc seconds at that distance corresponds to about 680 meters. So we really nailed the position of this asteroid extremely well, and that was enough to give us a strong detection of the Yarkovsky effect, which is something we've been expecting to see now for a while, and been acquiring more observations since it came out of solar conjunction in 2018. So I think it's probably worth providing a brief explanation as to what is Yarkovsky acceleration. It arises from non-isotropic thermal radiation. Basically, the heat that an asteroid radiates gives it a very tiny push. So the warmer hemisphere would be pushing slightly more than the cooler hemisphere, and that causes the asteroid to drift away from what a purely gravitational orbit would predict. And why is the Yarkovsky effect so important for Apophis? Well, this asteroid has numerous impact scenarios for the second half of this century. Back when it was discovered in 2004, it looked like it had a roughly 3% chance of colliding with the Earth in the year 2029. But additional observations quickly ruled that out, but it did show that the asteroid was going to come very close to the Earth. In fact, it will pass within the belt of communication satellites, and it will be as bright to be seen with the naked eye. If you're familiar with the Big Dipper, that star that connects the handle to the Dipper is about a third magnitude star, and that's how bright the asteroid will become in 2029 on, of all dates, Friday the 13th in April. April 13th is when the flyby will occur. So you need to take into account the Yarkovsky acceleration when you compute the impact risk. Okay, so on the left here is a diagram that was published back in 2015 by Volker and his co-authors. And on the right-hand side of that figure are a couple of gray bars, and that represents where the asteroid would be if we took gravity only into account. And there are some so-called keyholes labeled there. A keyhole is basically the distance from the Earth at which the asteroid would have to be in order to produce a future impact. This would be the keyholes in the year 2029 during that close approach. So if it passes at just the right distance from the Earth, the gravitational pull of the Earth will change the orbit by just the right amount to have it come back and hit the Earth in some later time. So on the far left of the diagram is the 2036 impact scenario, which we've been able to rule out now for some time. And the 2068 impact scenario is shown there toward the right-hand side. And if you take only gravity into account, you can see that the orbit is known well enough to where you could say that the Earth would be safe from an impact in 2068. But once you take the Yarkovsky effect into account, that shifts things towards the left a little bit, and that black curve is what they predicted from the uncertainties in their models. That's what they predicted as the range of possibilities. And as you can see, the 2068 impact scenario is included. So another figure from their paper in 2015, the gray curve labeled number 1 is what they were able to detect in terms of Yarkovsky acceleration using the data that were available as of 2015. As you can see, it's a very uncertain value there, and it includes 0 as a possibility. So the data just weren't good enough as of 2015 to detect the Yarkovsky acceleration on this asteroid. And then the curve in gray labeled number 2 is what they predicted would be the case based on what we know of the rotational model of the asteroid, based on reflected light observations. It changed its brightness periodically, and they were able to determine the rotational state of the asteroid. And also the thermal properties have been measured as well. So you combine those two things and you can make a prediction for what the Yarkovsky acceleration ought to be. And as you can see, that gray curve peaks at a value of around -26 times 10 to the -15th astronomical units per day squared. Whoops, let me back up here. Yes, okay, so -26 is what they predicted, and our measured value is actually -27 times 10 to the -15th, give or take 2. So our one standard deviation range is from -29 to -25, and so it very nicely brackets the prediction from their 2015 paper. And that basically means that the 2068 impact scenario is still in play. We need to track this asteroid very carefully. Obviously, the 2029 close approach is critical. We'll know after that occurs exactly where it was as it passed the Earth, and that will make it much easier for us to predict future impact scenarios. Okay, so there's my contact information. If you like more information, send me an email at tholen@ifa.hawaii.edu. That's all. Thank you.
Hi there. I'll be the last presenter today for this session. My name is Ronald-Louis, and I'm a postdoctoral scholar at the Lunar and Planetary Lab at the University of Arizona. I'm also a member of the science team for the OSIRIS-REx asteroid sample return mission. Today, I'm happy to share our discovery of craters on the asteroid Bennu's Boulders. Our work on this topic was published today in Nature, so please look out for that article. So just a quick overview of the OSIRIS-REx mission. OSIRIS-REx spacecraft is visiting the carbonaceous asteroid Bennu. Bennu may contain the molecular precursors to the origin of life and the Earth's oceans, so it has a lot of scientific interest. Some of the OSIRIS-REx mission's key science objectives also include mapping the asteroid and documenting the sample site. In the course of looking for material on the surface of the asteroid that were small enough to enter the sampling container, we obtained unprecedented detail of the surface of an asteroid. It was during a particular survey called Orbital B, that, as we show the diagram on the right, that we obtained a centimeter per pixel scale resolution images of the surface. Furthermore, the OSIRIS-REx laser altimeter, or OLA for short, which was contributed by the Canadian Space Agency, created 3D maps of the surface. OLA is a LiDAR instrument. A LiDAR is similar to radar, but uses laser light instead of radio waves to measure distance. In these images, we discovered craters on the boulders, which we likened to bullet holes. These range from as small as 3 centimeters and as large as 5 meters. It was a bit of a surprise that we found these. We expected that there should be craters on boulders, but we didn't know if they could be clearly identified as we see here. Boulders of this size on the Earth don't show these impact features because our atmosphere burns up the meteoroids that would create craters of these sizes. So we typically only see much larger craters in these sort of 100-meter scales or greater. The image to the left shows their bullet hole-like appearance of these craters, and the image on the right is of the largest such crater on a boulder. Note, though, that there are much larger craters on the surface of Bennu, up to 200 meters in diameter. We later confirmed that these were craters by using detailed topographic measurements returned by OLA. The color in the left-hand images show the height from the highest point of the center of the crater, which we typically refer to as the crater rim. It gives us this unprecedented view of the surface of the asteroid. Craters on solid rocks on extraterrestrial bodies were last measured on Apollo samples. Since then, we've visited other asteroids, but we've never had quite the same level of detail for images and topographic information as we do with the OSIRIS-REx mission. For example, this lunar sample here, as reported in Hortz et al., shows a millimeter size impact crater. So what can these craters tell us about the properties of both the target and the projectiles that made them? So we developed this technique to quantify the strength of solid objects using these craters. Suffice to say, we looked for what the limit was for crater formation for a given size of boulder. And from this, we were able to get an estimate of the compressive strength of boulders of arbitrary sizes. For Bennu, these were 0.5 megapascals, which we liken to chalk. Granite, for example, has 100 megapascal strength. Secondly, we can use the boulders as witness plates to understand Bennu's history. And we found that, by measuring the size of these craters and the surface area of the boulders, that these boulders have been exposed to impacts for about 1.75 million years. So what are the implications for these results? First, the strength result. As reported by the NEO Science Definition Team, a catalog that is about 90% complete for potentially hazardous asteroids larger than 140 meters would correspond to characterizing 90% of the impact threat of subglobal effects to Earth. For example, the Chelyabinsk meteor fireball, which entered the atmosphere in Russia, was 20 meters in size, which is comparable to the boulders that we see on the surface of the asteroid. The largest boulder observed on an asteroid like Bennu was the Otohemia boulder on Ryugu, and that's 160 meters in size. If this boulder were to enter Earth's, of a boulder of this size would collide with Earth, it would cause a catastrophe. So characterizing these strengths is super important. Secondly, our result that Bennu's boulders have been exposed to impacts for 1.75 million years. Why is this important? Basically, we found that this tracks Bennu's lifetime as a near-Earth asteroid. So it sort of validates decades of theoretical studies that show the short lifetimes of NEAs, or near-Earth asteroids, compared to the age of the solar system, requires that there is a reservoir for them. They must come from somewhere, which is the main asteroid belt. This age represents the last time Bennu was, escaped from the main asteroid belt and has been a near-Earth asteroid. So in summary, we report on the discovery of craters on asteroid Bennu's boulders, and we developed a technique to quantify the strength of solid objects using remote observations of craters. And we use these to basically get Bennu's lifetime as a near-Earth asteroid. So please see our work in Nature that was released today for a more detailed description of this work. And I'd like to acknowledge that this work is supported under the New Frontiers program by NASA. And I'm grateful for the entire OSIRIS-REx team for making the encounter with Bennu possible. That's my contact information at the bottom if you'd like to ask me questions. Thank you.
All right, thank you for the presentations. Can all the panelists please turn on their microphones and videos? And Rick, do we have any questions?
Yes, we do have a couple of questions queued up. These are both from Govert Schilling, a freelancer in the Netherlands who's currently writing for Sky and Telescope. The first question is for Tracy Becker. There are indications for a lower density of Psyche, see Lori Siltala's talk of today, lower than iron meteorites or planetary cores. What does that tell you about the hypothesis that Psyche is a planetary core?
Thanks for the question. Yeah, so I think it tells us, one, that we really do need to get a close view of this asteroid to really understand fully everything about it. I think that the main point of some of these recent studies coming out that kind of possibly counteract or question the idea that perhaps it's more of a solid core. I think one thing you can always keep in mind too is that when it comes to the density, this doesn't have to be a completely intact metallic core. It can also have a lot of open spaces in it as well that could be contributing to its lower density that some of the measurements are implying. There could be mixtures with other rocks and other material. I don't think that necessarily rules it out as a core either. That said, I think all of the compilation of evidence is what's really kind of making it more and more intriguing as we get closer and closer to the mission. From the UV perspective, we really are only sensing the very top of the surface. So we can't necessarily say anything else about what the entire body must be. But like I said, in the UV at least, it seemed to support that there's at least some metal, if not a lot of metal. But again, it's going to really depend on what the whole thing is actually made of to really figure out whether or not this is representative of a planetary core.
Okay, thank you for that answer. Govert's second question is for David Tholen. Did the Vok-Hrulicki et al. Predictions for 2068 impact, where they showed an impact probability of 6.7 times 10 to the minus 6, include their prediction for the Yarkovsky effect? If so, does that mean that your detection of the effect does not change anything on their impact probabilities? Or do we now have another, and perhaps better, impact probability for 2068?
The quick answer is yes, it did include the Yarkovsky effect. If I were to bring up that figure again, you recall those gray bars at the right-hand side. That was the gravity-only situation, and it nicely excluded the 2068 impact scenario. So if it had been gravity only, then the impact probability in 2068 would have been 0. So the 6.7 times 10 to the minus 6 impact probability does include the Yarkovsky effect. And the the width of that black curve in that figure basically reflects the uncertainty in some of the model parameters that they were using to make the prediction. For us, the width of that curve is going to be based on the range of values that are consistent with our observations. And that is a number we're still in the process of refining because of the effects of chromatic dispersion. Basically, the Earth's atmosphere acts like a prism. And so if the color of the asteroid is slightly different from the color of the reference stars that you're using to determine the position of the asteroid, it can introduce a slight systematic error. And that was the problem we had back in 2018. We were able to detect this chromatic effect, and that was limiting our ability to detect the Yarkovsky acceleration. The super observations in January and March were done when Apophis was very high in the sky. They were done with a filter, and so the chromatic effects are really minimal. And so those observations aren't nearly as affected by the chromatic effect as the older observations. It's the older observations that we're a little bit more concerned about. And one of the things that we did to try and determine whether we were being fooled by chromatic effects was to look at different subsets of the data where we eliminated the observations made lower in the sky. And the Yarkovsky acceleration that we measured was pretty constant, but the error bar got bigger as we threw out more and more observations. And so the breadth of our curve is critically dependent on which observations we include in the analysis. So that is what's going to control the impact probability based on our measurement of the Yarkovsky acceleration. Hope that answers your question.
Okay, thanks very much, Dave. We've got a couple more questions have come in. I'm pretty sure these are from fellow planetary scientists rather than journalists, but I could be wrong. First one, both of these are for Ron. First one is from Abedin. Your surface age estimate of Bennu, does it assume a constant impactor rate? What is the exponent value of the impactor size distribution in the range of observed microcraters?
Thanks, that's a great question. It does assume a constant impact rate for the last almost 2 million years. And we use the flux that was measured by Brown et al. And colleagues in the early 2002 to get at the age of the surface of these boulders specifically. The exponent of what we measure is a negative 2.7 in the cumulative frequency. Sorry, that's very specific. Very similar to what we observe from fireballs and tides on Earth. So we assume that all these craters were formed in near Earth space. And that's how we tie it specifically to when Bennu decoupled from the main asteroid belt and became a near Earth asteroid. I hope that answered your question.
Okay, and the second question for you, Ron, is from Derek Richardson. He asks, is the implication that Bennu formed only a couple million years ago from reaccumulation following, is the implication that Bennu formed only a couple million years ago from reaccumulation following the disruption of a larger body?
Thanks, Derek. That's a great question too. Like I said, the implication is that this is the age of Bennu as a near-Earth asteroid. When it formed as its own, as a near-Earth asteroid as an asteroid, but in the main asteroid belt is different. It's likely more than 10 million years old and up to a gigayear based on what we can see from the larger craters on Bennu.
Okay,
thanks,
great.
Derek.
Thank you. I actually have a question for Eliot. If I heard you right, you mentioned that the fact that Pluto's atmosphere is still more inflated than we might have expected, given that it's continuing to recede from the sun, the implication is that there might be some sort of heat source. And I'm wondering if there's anything about that inference that's consistent with, or that perhaps provides additional evidence for something that's potentially keeping a liquid ocean under Pluto's surface. I mean, in other words, that presumably requires a heat source as well. And I'm wondering if they might be linked in some way.
So when I said heat source, I was really thinking of a thermal wave that's propagated into Pluto's subsurface, and only now are we starting to see the heat come out. It's kind of the same reason why the hottest time of day isn't 12 noon, it's probably 2 in the afternoon. Thermal inertia makes a difference. And so the depth to which the thermal wave propagates and the amount of time it takes for the heat to come back out tells you something about the conduction of the subsurface, probably at the scale of meters at the most. You know, how good an insulator is it? So I suppose it could make some difference, but off the top of my head, I would be surprised if it could be important enough at that shallow level to make a big difference for keeping an ocean or not keeping an ocean. There's one other factor that's important to mention, and that is almost all of the atmosphere depends on nitrogen ice over one region, Sputnik Planitia. And there's that region is probably a deep enough reservoir of nitrogen that we're seeing convection, not very fast convection, but convection going on in that in that reservoir. And so that has to affect the rate at which heat comes out also. As far as primordial radiation and other heat sources that you'd expect that would be intrinsic to the planet, I don't know if what we learn about the surface properties near the surface are all that relevant in terms of whether you have an ocean or not. So that's a good question. I wish I could give you a conclusive answer.
Okay, thank you. So at the moment, the Q&A box is empty. So I think we may be nearing the end of the briefing. I'll turn it back over to you, Shantanu.
Okay. Thank you to all the speakers and everyone in the audience today. And thank you to all the PIOs who helped with the press releases and the briefings. Everyone else, please look out for all the press releases coming out from today's talks. And we'll have another session tomorrow. It's slightly earlier. It's at 11 a.m. Eastern time, so 8 a.m. Pacific. And we'll see you then. And for the panelists, if you can provide the briefing slides to Rick, if you haven't already done so, that would be great. And thank you very much. Bye-bye.
Thanks.